Okay, so let's take a look at the textbook. We're on page 149. Okay, so figure 2.4.5, which is the figure just down here, okay, shows 4 possible enthalpy-entropy combinations that could occur if you have a chemical reaction, okay? So let's look down here. Number 1, the enthalpy and entropy could both increase. So that would be, I'm going to put numbers in these boxes. So this is number 1 here. And you'll notice that as you're going in this direction, this is a positive enthalpy because that's an endothermic direction, okay? And then if you look at the particles, I'm gonna highlight the particles because it's easier to understand. So these are really ordered, and this is disordered, okay? So that means that as you go in this direction, the entropy is increasing. Okay, so that's number 1. Number 2, they could both decrease. So this is number 2 here. So as you go in this direction, we have a negative delta H, and this is an exothermic direction. That's why your delta H is negative. And then if you look at the particles here, this is where they are disordered, and this is where they are ordered. So in this direction, we have a decrease in entropy. The third option, one could increase and one could decrease. Now, there's actually 2 different variations of that. So I'm just gonna put a number 3 and a number 3 here, and I'm gonna explain the differences, okay? All right, so this is disordered. This is ordered, ordered, and disordered. Okay. So as you're going in this direction here, this is a positive delta H because that's your endothermic direction. Okay. And this is a negative delta S because you're becoming more ordered, or your entropy is decreasing. I'm going to make that note up here that a negative delta S means decreasing entropy. Okay. Over here, as I go in this direction, this is a negative delta H because that's the exothermic direction. And then this direction is a positive delta S because you're becoming more disordered. Questions on that? Okay, now, based upon those situations, okay, these are the descriptions of what you have, okay? So virtually no reaction will occur under this scenario here. this reaction goes to completion, what that means is you're pretty much going to have a lot of product. And this over here means you're going to have a lot of reactant, okay? And then in order for you to be at equilibrium, you'll notice that these two scenarios here, number 2 and number 1, are the scenarios at which you will be at equilibrium, okay? Let me know when I can go on. I'm assuming we're good. Okay. Let's come down here. Maximum entropy happens just shy of a completed reaction because if the entropy of the products is greater than the entropy of the reactants, a mixture containing a very small amount of reactants will have greater entropy than the products alone. So when we say that something goes to completion, that means the equilibrium mixture consists of very nearly pure products. Okay, so that's what this is referencing up here. Okay, likewise, even if both drives are towards reactants, a mixture containing a very small amount of product will have greater entropy than the reactants alone. So chemists say that a reaction does not occur because the equilibrium mixture consists of very nearly pure products. So this is what is being referred to up here. Okay. All right, all we need to talk about now is spontaneous processes, and then we're done. Spontaneous processes are ones that just happen on their own, okay? And there's no outside intervention. Chemical systems tend to move spontaneously towards equilibrium. So it just kind of like naturally happens. Let's turn to the practice problems on the next page. Okay. They want us to state whether equilibrium will have a reasonable proportion of reactants and products, whether it will go to completion, or whether it will almost not occur. And this is based upon the delta H value and the delta S value. So here you'll notice that your delta H is positive. That means this is an endothermic process as it is written. So that means that this direction is a positive delta H, okay? And then if you take a look at the states of matter, here you've got your gases, okay? And you've got 3 gas particles here and 2 gas particles here. So that means that in this direction, you've got a decrease in entropy because the number of gas particles decreased. So if we're thinking about this in terms of delta H and delta S, this direction is your negative delta H, right? Which is the direction that we're concerned with. And this direction is the increase in entropy. So if you've got both of them driving towards the reactant, so both your delta H and your delta S drive towards the reactants, okay? And this is observed on the previous page, I believe. Let me look. We've got positive delta H and negative delta S. So that means you're looking at this one right here, okay? So this is virtually no reaction, okay? So this will almost not occur, okay? Okay, now for number 2, this reaction at equilibrium has a reasonable amount of reactants and products, and they want us to state whether this reaction is endothermic or exothermic. Okay, so let's take a look first at the states of matter, and then we need to look at the previous page to figure out which one of those categories it is that we're kind of looking at. So if we have a reasonable amount of reactants and products, that means that you are at equilibrium. So you're going to have negative delta H in one direction, and you're going to have positive delta S in the other direction. So I'm just going to make a note that this means that negative delta H is in one direction, and your positive delta S is in another direction. Okay, so that means we need to figure out the delta S, because that's going to help us figure out what direction the other one is in. So CO2. Okay, so if you take a look, I don't think I have a different colored highlighter here, but if you take a look at the oxygens, okay? Do you see how you've got the oxygen here in one molecule, and then now the oxygen is in 2 different molecules here? So I'm just going to make a note that you've got the oxygen in one molecule here. And then the oxygen in 2 molecules over there. So that means that if you go in this direction, this is your increasing entropy direction. So in order for us to have a reasonable amount of reactants and products present at equilibrium, your delta H has to be in the opposite direction. So this is the direction of your negative delta H. That tells me that as you're going to the right, that this is going to be an exothermic process. Okay. And then number 3. The following equilibrium also has a reasonable amount of reactants and products. That means that negative delta H is in one direction and the positive delta S is in another direction. State whether entropy increases or decreases in the forward reaction. So you've got your exothermic reaction in this direction because your delta H is negative. So that means that you have to have your positive delta S going in the opposite direction. So if your entropy is increasing in the reverse direction, then that means that the entropy has to be decreasing in the forward direction. And that's it.